All right, we should be live. And for those of you who are physically here at Columbia, then Tiffany is here. So when we celebrate, we can actually celebrate in person outside, just as a heads up for later. So it looks like we still don't have Tiffany. Perfect timing on your PhD defense to restart your computer and have debugging. Is Harper the dog? That's the little dog, right? Rose is saying, let Harper do the talk. Okay, we're just waiting for Tiffany to come back. If you're just joining on, she just had to restart her computer. Her video wasn't working. I think the backup option will be she'll maybe share her screen without the video, which should be fine. I can see some family members who are here. Welcome. We're just waiting for Tiffany to come back on. And everybody, obviously, many of you are Zoom pros, but please do mute yourself during the talk. Time for questions at the end.
There's another bathroom straight back to my on electronics.
Actually wondering if I should go up and check. Oh, she's back. Okay, perfect. Hi, Tiffany, you back on? Okay, we can see you.
Okay.
We can hear you. There we go.
My computer's being ridiculous. Of course, it chooses today to be.
Okay, never mind. Panic over. Everybody's here. All right, so I can get started with the introduction. It's my pleasure today to introduce Tiffany Jansen, to whom I've had really the great pleasure of mentoring over the last, I think, was it 5 years now? It's obviously always a really proud day for an advisor when their student completes their PhD. It's the highest obtainable degree. I always like to emphasize that because it's, it's nice to put that on your CV. But such days are, they're also somewhat bittersweet for me as an advisor, because now, after all, who else am I going to geek out with about Star Trek and Tolkien lore? During her PhD, Tiffany has amassed a very diverse range of skills, really exceptional, organized around this central theme on exoplanet phase curves that she's going to tell us about today. And that ranges from theoretical modeling, time series analysis, software development, statistical regression. And I think even probably Tiffany doesn't realize just how rich her skill set has evolved over the last half a decade. Of her many scientific achievements, one I'd like to highlight that I predict that she'll probably mention is the first observational albedo constraint of a Neptunian ensemble and a terrestrial ensemble of exoplanets. First time that ever happened, using an innovative statistical technique. And I think still today there is no other comparable measurement that's been achieved. I know that Tiffany has a very exciting future ahead of her and seeks to use these skills beyond academia now, but wherever she goes, she will always be welcome at the Cool Worlds Lab. And so with that, I'd like to hand over to Tiffany as she presents to us today some highlights from her PhD.
Oh, thanks, David. That's really nice. Let's see here. Okay, I'm now sharing my screen. Can you all see it?
Got it.
Excellent. Okay, so hi everyone. Thanks so much for coming to my the public portion of my dissertation defense. I'm very excited to get to share my work with you all. It's been such a joy to get to dedicate this part of my life to studying planets around other stars and to get to contribute new information to our knowledge of the universe around us. Of course, it wouldn't have been possible without the help of so many others. Firstly, I'd like to say thank you to my advisor, David Kipping, for his support and guidance over the years, and of course, the Trek chats. And to the rest of my thesis committee for taking the time to read my dissertation and come together to have a fun chat about it. I'd also like to thank my family for always welcoming me home when I needed respite from the city. And lastly, I'd like to thank my husband, Andrew Fox, for his endless support in this crazy journey. Okay, so I'll start out by giving some background just to get everyone kind of on the same page here. So in the history of astronomy, the study of planets around other stars, otherwise known as exoplanets, has only really just begun. Prior to the 90s, it was thought that planets probably existed around other stars, but we couldn't know for sure, having never actually observed one. The first exoplanet orbiting a sun-like star wasn't discovered until 1995, thanks to advancements in methodology and instrumentation. And since then, more than 4,000 exoplanets have been discovered using various methods. The properties we've learned about these planets have primarily been derived from the light we collect from their stars, and rarely from light that has been reflected or radiated from the planets themselves. Their size and their mass, the length of their years, and their distance from their stars are all derived from the periodic loss of flux received from the star as the planet shadow is cast in our direction. Otherwise known as the transit method. It's actually incredibly difficult to observe light coming directly from a planet because stars are generally millions of times brighter than their planets. And it's like trying to spot a candle way in the distance when you have a giant spotlight right in your face. Sometimes in special cases, you can block the light of the star, like what's being done in this video, kind of like you do with your thumb to the sun, but this is actually really difficult to do, and it only really allows you to see planets that are far away from their stars, which tend not to be bright enough to see. In some cases, a planet will be close enough to its star that it will reflect and radiate enough light that it can be distinguished from the star's light. So when we watch this planet orbiting its star, we are watching the illuminated portion of the planet wax and wane through its phases, much like the phases of the moon. If the planet is highly reflective, or if its day side is hot enough that it glows, the amount of light we collect will periodically increase and decrease in time with a period equal to the orbital period of the planet. And this is called a phase curve. To separate the light of the planet from its star, you have to come up with clever ways to remove the star, which I'll talk about more in a bit. So here is a simple illustrative example of a planetary phase curve observed in both the visible and infrared spectrum. The surface of this example planet reflects symmetrically such that it appears brightest on the opposite side of the star in opposition to us, but it also absorbs some of its star's light, which produces a thermal hotspot centered on the part of its surface that is directly beneath the star, which we call the substellar point. The blue line is the phase curve we would observe if our telescope could only see in the visible part of the spectrum, while the red curve is what we would observe in the infrared. But the instruments I've worked with for my dissertation observe in both of these wavebands, in which case we receive photons from both visible and infrared wavelengths at the same time, which is what you see in the black line. Okay, so what can we learn about planets from their phase curves? Why do we care about phase curves? Well, the reflectivity of an object says a lot about what its surface is made out of. For the record, when I say surface, I mean the layer that we can see. On planets with atmospheres, this will be at a certain depth in the atmosphere, while for rocky planets without atmospheres, the surface is, well, the surface. Venus, for example, is the most reflective planet in the solar system because it's covered in highly reflective clouds, sulfuric acid droplets, while Mercury is the least reflective object due to its lack of atmosphere and rocky surface. On the other hand, a gaseous planet with a low reflectivity indicates the presence of particles in the atmosphere that absorb strongly in the bandpass in which the observation is made. But a really big dark planet can reflect as much as a smaller, more reflective planet. So how can we tell which is the case? Well, by measuring the size of the planet and how far it is from its star. The radius of a planet can be measured if the planet is transiting its star, in which case the amount of stellar flux that gets obscured by the planet is directly related to the size of the planet compared to the size of the star. As for the orbital separation, Kepler figured out that the separation between a planet and its star is proportional to the star's mass and its orbital period, which we can also measure from the amount of time between each transit. Okay, so having derived the radius and orbital separation from the transit light curve, you can theoretically derive the geometric albedo of an exoplanet by measuring the amount of light lost when the planet moves behind the star, otherwise known as the occultation. But the geometric albedo is a really specific measure of reflectivity since it's defined to be the ratio of the amount of light reflected by the planet at full phase to the amount of light that would be scattered off of a fully reflective and perfectly diffusing disk. Observing a full phase curve rather than just the amount of light lost when the planet moves behind the star is beneficial in a couple of ways. First, it provides much more data to work with, which helps suppress observational noise, but it also allows us to constrain the more informative bond albedo, which is defined to be the fraction of light hitting its surface that gets reflected back into space. So observing how the brightness of a planet varies throughout its orbit can tell us a lot about the composition of its surface. For example, Cassini observations of the full phase curve of Titan show that this Saturnian moon actually appears brighter when back illuminated than when fully illuminated, which is due to the size of the particles in its extended hazy atmosphere. So by observing full reflective phase curves of exoplanets, we can begin to constrain the size and therefore type of condensates in the types of atmospheres not found in our own solar system. So the first thermal map of an exoplanet was made possible with observations of the full phase curve of the hot Jupiter HD 189733b. For planets that are very close to their stars, which, by the way, are all the planets I'll be talking about today, the gravitational forces of their stars are expected to show a planet's rotation until one side is always facing the star, for the same reason that we only see one side of the moon. If winds in the atmosphere of a tightly locked planet, as we call them, carry hot air from the day side toward the cooler night side, the hottest region on its surface will not actually be directly under its star. In this case, the brightness maximum in the phase curve will not occur where we would expect it to, Instead, the hottest region will be facing us, the observer, at some other point in its orbit, which indicates there are substantial winds in the atmosphere of this planet. So in summary, we are motivated to observe the full phase curves of exoplanets because they theoretically provide insight into the compositions of their surfaces or atmospheres, distribution of clouds, continents, or other varying surface compositions, temperature contrast between day side and night side, and therefore something about the weather conditions on planets outside of the solar system. But obtaining a full planetary phase curve isn't as easy as just pointing a telescope at the system and observing. Phase curve signals are relatively small compared to the variability of stars and telescope systematics. So it's important to remove or account for these nuisance signals, as we call them, before trying to measure a planetary phase curve, which we call detrending. Conventional detrending methods for transit analysis are not really well suited for phase curve studies since phase curve signals occur over much longer timescales, which requires far greater long-term stability in the final data product. One popular method to remove nuisance signals is to fit a series of cosines or polynomials to the data, but over phase curve timescales, higher and higher orders are needed to adequately fit the data, which quickly becomes unstable. So we approach this by coming up with a new method. So my first year here at Columbia, David and I developed a new detrending method specifically for phase curve analysis, which we call PHASMA. So PHASMA takes advantage of the fact that phase curves repeat in a very predictable frequency, with a very predictable frequency. Because the phase curve is a product of the planet's motion about its star, it repeats every orbital period of the planet, which we know to great precision for a transiting planet with no other companions in the system. Therefore, the median value of a repeating signal over one cycle is constant for every window of data spanning one orbital period. If other nuisance signals are present and are not in phase with the planet, that is, they don't repeat with the same frequency as the planet's orbital period, the median value of the nuisance signal will not be constant in time, which allows you to draw out the nuisance signal while leaving the phase curve unaffected. So this will make way more sense with an example. So I've created some fake data to show PHASMA in action. In the top panel, I've created a fake planetary phase curve in blue, which is what we want to retrieve, and a fake nuisance signal in orange, which is what we want to get rid of. So this is like a star with a star spot and some flares, small flares. Of course, when we observe the system, this all comes blended together and also with some observational noise. So if we zoom in, we can see the planetary signal a little better, which is this black wave. So imagine first if we applied this moving median to a simple sine wave oscillating around 0, where this moving median has a width equal to the period of the sine wave. The median would just be equal to 0, since there are as many positive values as negative values in one complete cycle. And now if you shifted the window over one data point, you still see one complete cycle. So the median value of the sine wave is still equal to 0. And if you keep doing this over the entire length of the repeating sine wave, you would end up with a straight line. So now imagine you have a sine wave with some nuisance incline that isn't due to a planet, like we see here in this example. The median value at every point in the purple box is now the average value of the sine wave plus the incline signal. So by taking the median of a chunk of data spanning one orbital period at every point in time, you can trace out the nuisance signal exclusively, which can then be removed from the observation. So now we can zoom back out and see PHASMA in action over the entire phase curve. You might notice that PHASMA doesn't pick up on the flares, but these will average out once we fold the light curve into a function of the planet's orbital period. Okay, so once you've traced out this nuisance signal, obtaining the phase curve is as easy as dividing the light curve by this nuisance signal, folding the light curve on the planet's orbital period, and binning the data into points in phase to average out any leftover sources the moving median and outlier removal didn't pick up on, so like small flares. So on the bottom is the fake noiseless phase curve I injected in blue, compared to the phase curve Phasma retrieved, which you can see does a pretty good job. And here we can see an example of Phasma performed on real Kepler data of the hot Jupiter HAT-Q7b. In the bottom panel, we see the Phasma phase curve in red compared to the analysis of Armstrong et al. 2016 in black, where the red in the top panel is the nuisance signal light curve that's drawn out by Phasma. So one of the main advantages of Phasma is that it's non-parametric. It only requires the orbital period of the planet, and it's more stable than higher order polynomials and cosine series. Because it's non-parametric, there's no risk of overfitting the model to the data, which runs the risk of removing some of the phase curve itself. This results in a more accurate, more physically motivated, yet somewhat less precise retrieval of the phase curve. And overall, Phasma is relatively simple and easy to implement. So much of my role in the development of Phasma was to create a Python package for using Phasma on TESS or Kepler data, which enabled the phase curve analysis in the next couple of chapters. So last year, David and I published our detection of the phase curve and occultation of WASP 100b with the Transiting Exoplanet Survey Satellite, which we call TESS. TESS is a space telescope that has scanned almost the entire sky in a wide photometric band that covers the 600 to 1,000 nanometer range. WASP 100b is a great candidate for a phase curve detection since it has a super short orbital period, less than 3 days, making it an ultra-hot Jupiter. And it's in TESS's continuous viewing zone, which means we were able to observe the planet for 76 of its orbits. As you might have guessed, we use Phasma to obtain the phase curve of WASP 100b. But to make sure Phasma doesn't produce something way outside of what we expect, we also detrend with the standard polynomial fitting method. And as you can see from the blue and orange points, the two methods agree quite nicely. And to account for any uncertainty in the detrending methods, we use the average phase curve between the two for analysis. Now, we want to interpret what this phase curve says about the surface of WASP 100b, but because of the wavelength range TESS observes in, it's not so easy as saying, well, the phase curve amplitude is this big, so it must be reflecting this much. Rather, we're likely observing both reflected light and thermally emitted light, and it can be difficult to measure them individually. For example, the Kepler phase curve of Kepler 7b produces what you see on the right, where Kepler's waveband overlaps quite a lot with TESS's, and the Hugh 2015 study shows that the phase curve can be modeled equally as well by a migrated hotspot as by a patch of clouds reflecting from the same longitude. So to break this degeneracy, you need to observe the same system with an infrared telescope in order to find out how much thermal radiation it's emitting. But that takes a lot of time and investment into a telescope. And fortunately, you can gain some insight into the thermal properties of the planet by measuring both its phase curve and occultation depth. So when a planet goes behind the star, the light from its day side gets blocked from our view, which we call an occultation. For a planet on a circular orbit, we see this as a drop in flux half an orbit after its transit, where this drop in flux is called the occultation depth. When the planet is directly between us and the star, we're looking at its night side, where no light is reflected from the surface. If no heat gets redistributed from the day side to the night side, we will also see no thermal emission during its transit, so the planet is completely dark. This results in an occultation depth equal to the phase curve amplitude. However, if the heat does get redistributed to the night side, we will observe thermal radiation emitted from this warm night side. Because the phase curve amplitude depends on the brightness contrast between the day and night side, the amplitude will be lower for a planet that has a warm night side than if it had a cold night side. The day side of a reflective planet is in general much brighter than its night side, so when the planet goes behind the star, both the thermal emission and reflected light from the day side gets blocked from view. So in the case of a warm night side, the occultation depth will be greater than the phase curve amplitude. So comparing the occultation depth through the phase curve amplitude and shape then tells us whether or not there are winds carrying heat from the day side to the night side in the atmosphere of a hot Jupiter. So luckily, we are able to measure a significant occultation depth of WASP 100b, where we measure it to be 100 plus or minus 14 parts per million, which is the average depth between 5 different methods, which adds an additional 16 parts per million of uncertainty. And I use this occultation depth later to help fit a phase curve model to the data. Okay, so now that we have the phase curve and occultation depth, how can I use them to measure the reflectivity and heat redistribution efficiency of WASP 100b's atmosphere? First, I use a mathematical model that describes the phase curve, which is determined by the physics and geometry of reflection and thermal radiation throughout its orbit. In its most simple form, the planetary phase curve is the sum of the thermal and reflection components, which I give here. But this is a lot to take in, so I'm not going to go into detail, but I'm just going to put it up for the record. And if you're curious about the details, you can ask me about it in the Q&A. But all I really want you to take away from this slide is the 3 parameters I'm trying to measure. The bond albedo, which is a measure of reflectivity, the thermal redistribution efficiency, epsilon, which controls how well heat gets redistributed over the surface, and the intrinsic thermal scaling factor, F, which just scales the temperature to account for heat from the planet itself, for example, from tidal heating. Okay, so I've coded up the model in Python. Now, how do I measure these parameters? First, I start out with a range of possible values these parameters could take. Then I pick random values from this range and measure how well this model fits the data. And I do this millions of times, or a computer does this millions of times, until I've reached a range of solutions that will produce a model that represents the phase curve well. For the astronomers in the house, I use the MC package to perform this MC analysis. And here are those solutions. On the left, we see the distributions of values the parameters can take to produce a model that represents the data well, otherwise known as the posterior distributions. On the right, we see about 1,000 models formed from samples from the posterior distributions, which the purple lines plotted with the observed phase curve of WASP 100b in black. There are a few parameters in the corner plot that I haven't talked about that account for signals from the star produced by the planet's influence on the shape and motion of the star, but unfortunately I don't have time to go into them, but they're really interesting, and so someone please ask about them in the Q&A. A really intriguing feature of the phase curve of WASP 100b is that it appears brightest before it passes behind the star. Intuitively, it makes sense that the hottest, brightest part of the planet would be the point that receives the most starlight, which is the spot that's directly beneath the star, the substellar point. Instead, assuming the planet rotates in the same direction that it orbits, the planet appears brightest when longitudes east of the substellar point is pointing in our direction, which is evidence that the hot air from the substellar point has been carried east by substantial winds. So observing such a large shift in the brightness maximum was a little bit of a surprise, especially since my results were the first to show this phenomenon with this telescope, because there has been some evidence from prior phase curve studies that hot Jupiters that receive more flux from their stars tend to also have larger temperature contrast between the day and night side, where it's thought that this may happen because radiation timescales decrease with higher temperatures. But there has been more evidence for efficient heat transport on hot Jupiters in subsequent studies with the same instrument, which adds more weight to our conclusions. One proposed mechanism to explain the shifted brightness maximum has to do with the recombination of hydrogen molecules. So the idea is that on the day side of these worlds, temperatures are high enough to break up hydrogen molecules, and when this hydrogen gas gets carried toward the night side, the temperatures cool down enough that the hydrogen recombines, which releases a ton of energy. So the thought is that perhaps what we're observing is this energy being released in the recombination of hydrogen molecules. Okay, so what about the smaller planets? Hot Jupiters like WASP-100b are relatively easy to observe due to their size, and very few phase curves have been observed for smaller planets. So how can we learn about these sub-Jovian surfaces? This brings us nicely to the next chapter. With the telescopes we have so far, light from individual sub-Jovian planets is indistinguishable from the noise in the data. One solution to suppress this noise is to get more data, since more data equals less uncertainty in your measurements. From 2009 to 2013, the Kepler satellite observed the same patch of sky for 4 years, collecting an incredible amount of data. But despite all this data, there have been very few phase curves observed of planets smaller than Jupiter, leaving their surfaces a mystery. Unfortunately, Kepler's mission has ended, so we can't use it to collect more data. But what if instead of trying to measure the phase curve of one planet, we combine the data from a bunch of similar planets and measure their average phase curve? In this way, we lose information about the individual planets, but we're able to gain information about the average characteristics of a type of planet in one ensemble. So to increase the odds of measuring an ensemble phase curve, I wanted to include as many planets as possible in the ensemble. So I started with all the known confirmed exoplanets and began making cuts from there. So first, I only include planets with orbital periods less than 10 days, since they will be the closest and brightest compared to longer period planets. And we choose planets around stars that have likely not evolved into giant stars, which have a higher rate of false positives and are generally more active. Then I want to group planets by similarity so that their different characteristics can be compared. There are basically two classes of planets smaller than Jupiter, those with substantial atmospheres and those without. We call planets smaller than Jupiter with substantial atmospheres Neptunian planets, purely because they are of similar size, though the composition of their atmospheres can be quite different than Neptune. Then the planets that are even smaller, those without substantial atmospheres, we call the Terran planets because they're more like Earth in size. So to classify a planet as either Terran or Neptunian, I use the forecaster package introduced in Chen and Kipping 2017 that uses prior observations of planetary mass and radius to assign a probability that a planet with a given radius is either terrestrial, Neptunian, Jovian, or star-like in nature. I chose planets that are at least 90% likely to be of the sub-Jovian type, then further categorize them based on whether they're more likely to be terrestrial or Neptune-like. This leaves us with an ensemble of 50 Terran planets and an ensemble of 115 Neptunian planets. Previous groups have done similar stacking studies, but only for secondary eclipses, not for full phase curves. Even though phase curves are more challenging to work with, you get an entire orbit's worth of data to analyze rather than just a small fraction of the orbit, which motivates our use of the full orbital phase curve. Furthermore, we take a more conservative approach to what is considered to be a rocky planet. Previous studies define the transition at 2 Earth radii, but there is more evidence that 1.75 Earth radii is more likely to be the transition. So using the forecaster package, our sample is split at even smaller radii at around 1.25 Earth radii, making the planets in our Terran ensemble much more likely to be terrestrial than gaseous. And from the points I've circled, you can see that our study is the first to constrain the average albedo of worlds that are very likely to be rocky. Okay, now that I have my ensembles sorted, how do I go about analyzing their phase curves? First, I remove outliers from the data and use PHASMA to detrend each individual light curve. And each light curve is then folded on the orbital period of their respective planets, which sorts all of the data into a function of orbital phase. Then this phase curve is binned into the same amount of points in order to prep for stacking. So after correcting for individual offsets, we take the weighted average of all the phase curves to obtain one ensemble phase curve for each type of planet, Terran and Neptunian. The rest of the process is similar in a lot of ways to how I analyze the phase curve of WASP-100b, where I sample a bunch of possible values of bond albedo, redistribution efficiency, and intrinsic thermal scaling factor until a range of suitable parameters is converged on. So for the Terran ensemble, even stacking 50 planets wasn't sufficient to measure any significant atmospheric characteristics. However, because I know the radii of every planet in the ensemble, I can at least constrain an upper limit on their reflectivity. In other words, if the average reflectivity was greater than a certain amount, we would detect the signal, but because we don't, the reflectivity can't be any higher than a certain amount. So I measured this upper limit on the Terran albedo to be less than 0.42 with 95% confidence. What does that mean? For context, Venus has a geometric albedo of 0.67, so I can at least conclude that the average planet in this ensemble is not covered in reflective clouds or hazes like Venus. Aside from an albedo constraint, I also find that the null detection constrains the thermal component to be less than 1.6. So this result is consistent with my conclusion that these planets are unlike Venus, which has a much greater greenhouse effect in its atmosphere. Instead, it's likely that the majority of these worlds do not have a thick atmosphere and are therefore much more similar to Mercury, which is consistent with the theory that these planets are much too small and too close to their star to retain their atmospheres. Instead, they're likely covered in dark volcanic rock. Since our study, there has only been one phase curve measured for a terrestrial world called LHS 3844b. But because those observations were done with the Spitzer telescope, which is in a different wavelength range than Kepler, we can't directly compare our Kepler bandpass terrestrial albedo constraint to their constraint on the infrared bandpass albedo. But nonetheless, they do find that LHS 3844b's phase curve, its phase curve amplitude is most consistent with a basaltic surface, old volcanic rock, which is in agreement with our conclusion that short period Terran worlds are much more likely to be Mercurian in nature than Venusian. So similar to the Terran ensemble, the phase curves of 115 Neptunian planets was also not sufficient to measure any significant atmospheric characteristics, although the uncertainty on the reflectivity is a bit smaller than for the Terran ensemble. Still, the significance is low, so upper limits are a more appropriate measure to report. And for the Neptunian ensemble, the upper limit on the albedo is set to 0.23, which means that the average planet in this ensemble is likely much less reflective than our own Neptune, which has an albedo around 0.3. This is consistent with the theoretical expectation for warm Neptunes to have a low albedo, both because the temperature of the atmospheres are likely too warm for bright clouds to form, and because the increased insolation on these short period planets can lead to more pronounced absorption in the Kepler band by elements like sodium and potassium. So I also try to gauge the presence of a measurable phase curve by computing the root mean square amplitudes of a sample of model phase curves from their posterior distributions, which is what is shown here. And as you can see, the Terran ensemble is consistent with a non-detection, but the Neptunian ensemble does show weak evidence for a non-zero amplitude. However, like I mentioned before, the evidence is weak enough that we only report upper limits. So in the rest of this presentation, I'll be talking about studying the atmospheres of exoplanets using a general circulation model, or GCM, which is a type of 3D computational model of a planet's climate. This model incorporates, as you can see here, a large suite of variables to explore. There are many different GCMs with their own capabilities, but for this chapter of my dissertation, I used NASA's Rocky 3D GCM, which differs most notably from other GCMs in its capability to model a dynamic ocean that's also coupled to the atmosphere. It's also capable of modeling different topographies, which affects things like river flow and runoff. What renders a planet habitable is, I skipped this. Okay, to examine how we can use these GCMs to model phase curves. I'll first start by demonstrating what a GCM can do with my study on the effect of a planet's day length and rotation rate on its habitability. Okay, now what renders a planet habitable? It it's highly debated topic in astronomy, but generally we all agree that the presence of a liquid solvent is crucial for the development of, and sustainability of life. On Earth, this solvent is liquid water, even though there are other possible solvents. We know for a fact that at least one form of life depends on water specifically, so a good first order gauge of the habitability of a planet is its ability to sustain a liquid state of water, which depends on the temperature. So how does rotation rate affect habitability? Well, it all really comes down to how rotation rate affects the dynamics of the atmosphere and large bodies of water, and in turn how that affects the temperature gradients and global average temperature. So what is the mechanism in which rotation rate affects the planet's habitability? For Earth's relatively rapid rotation, the Coriolis force breaks up the atmospheric transport into multiple convection cells. But for slower rotators, the Coriolis effect is not as strong, which allows the warm air from the equator to extend over a larger surface area, which effectively increases the temperature in the higher latitudes. This effect has been known for quite some time now from 1D climate models, but it's only recently we were able to study this effect in 3 dimensions, that being latitude, longitude, and altitude. So in 2014, Yang et al. Used the CAM3 GCM to study the effective rotation rate on the inner edge of the habitable zone, where they found that the global mean temperature decreased for slower rotating terrestrial planets. And I'll explain more why that is later, but we can also see that slower rotation causes clouds to gather at the substellar point, which increases a planet's albedo or reflectivity, effectively keeping the surface cool. So in 2019, I used a suite of rocky 3D models from Mike Way to study the effective rotation rate on what we call fractional habitability, which we define to be the fraction of surface area that can maintain liquid water. Because if there's potential for more liquid water, the possibility of forming life also increases. So we look at an Earth-like world with the same topography and land and ocean distribution, same radius, but with no obliquity or oxygen, so no seasons and no vegetation. But these models do have a nitrogen-dominated atmosphere, like the Earth. So what I find reflects previous results that the global average temperature decreases with slower rotations. The reason this is a couple of things. There's an increasing albedo from the increasing cloud coverage, which keeps the surface cool, but since the days are longer, the nights are also longer, which means the night side gets significantly cooler, which leads to lower global average temperatures. Because I use models with smaller rotation period increments, we're able to see that the fraction of liquid water capable surface area peaks for a rotation period between 8 and 32 days, at least for the 1 Earth solar flux model. This is due to a dynamical regime change that occurs at these rotation periods for an Earth-sized planet. For a planet rotating slower than Earth, the Hadley cell extends and carries warm air from the equator over a larger area, effectively warming the higher latitudes. But the Hadley cell can only extend so far, at which point the dominating heat contrast becomes diurnal, and the night side significantly cools with increasingly long nights, while cloud coverage and therefore reflectivity continues to grow about the substellar point, which keeps the planet cool. This results in a peak in the amount of surface area capable of maintaining water in a liquid state at rotation periods where this dynamical regime change occurs. And the rotation period at which the dominating energy transport mechanism goes from equator to poles to day to night will be different for a planet with different radii. So we also explored the effect rotation has on the carbonate-silicate cycle and its feedback mechanism. Very basically, the CO2 in the atmosphere combines with water vapor and it rains to the ground, where it reacts with the calcium and silicate carbonates to make carbonic acid, which is then carried to the ocean via underground runoff and rivers. Then cute little organisms in the ocean use this calcium and carbonic acid to make their shells, which sink to the ocean floor when they die. And these calcium carbonate shells are then subducted, broken down back into CO2, which is outgassed back into the atmosphere through volcanoes. So if your volcanic activity and other outgassing mechanisms stay the same, more weathering means more CO2 is sucked from the atmosphere faster than it can be replaced from outgassing. All that to say, more weathering equals less atmospheric CO2, and less CO2 means less greenhouse gases, which leads to cooler temperatures. So to quantify the silicate weathering rates, we define a weathering rate that depends on the amount of runoff and ground temperature in each grid cell of the 3D model. And we set this relative to the weathering rate of the modern Earth, modern insolation model. And from these GCM simulations, we can see that precipitation over land peaks between rotation periods 2 to 8 times that of modern Earth, and the average soil temperatures continually decrease with longer days. So this results in a peak in the weathering rate for rotation periods between twice and 8 times that of modern Earth, which is important for long-term habitability because it controls how much CO2 is in the atmosphere for a given outgassing rate, and therefore acts as a kind of greenhouse feedback, which plays a huge role in long-term temperature stability. And it's all really due to the interaction between the extended Hadley cell and how the landmass is distributed. For the solar rotators, water vapor gets carried to higher latitudes where it then precipitates. And in modern Earth's case, landmass is more concentrated in these northern latitudes. And all other things being equal, more precipitation over land equates to more runoff and therefore a faster weathering rate. Of course, unless the universe is infinitely large, no other planet is going to have the exact same continental distribution as Earth, but it is at least very possible for land masses to concentrate in higher latitudes, so the idea stands. And it's interesting to think about how the size and placement of a planet's continents can affect its climate. So we can also use these 3D GCMs to model the phase curves that we might expect to observe for existing exoplanets in their habitable zones, like some of the planets in the TRAPPIST-1 system, which is exactly what I did in the remainder of this dissertation talk. In 2015, astronomers announced the discovery of 3 Earth-sized planets transiting a very small M-dwarf star. A couple of years later, 4 more planets were found. We may have 8 planets in our own solar system, but finding so many planets around another star is actually pretty rare. And what's even more exciting about this system is that they are all Earth-size, of which 3 are at just the right distance from their star that water neither boils away nor entirely freezes. So earlier this year, I co-authored a study published and led by Professor Stephen Kane at UC Riverside, where we used the Rocky 3D GCM to simulate the atmospheres and surface conditions of TRAPPIST-1E and F to predict the observability of the phase curves these habitable zone worlds might produce. So for these models, we consider 3 planetary configurations: a TRAPPIST-1E size planet with an atmospheric composition like modern Earth, another TRAPPIST-1E size planet with a different atmospheric composition, one more like Archean Earth, and a TRAPPIST-1F size planet also with a modern atmospheric composition of Archean Earth. The surface in each simulation is entirely covered in oceans, and they're all tidally locked to their star, and the output radiation we use for the phase curve model spans both the visible and infrared wavelengths. So these are the resulting outgoing radiation maps of the top of the atmosphere of each simulated planet, where we have reflected light on the left and thermal emission on the right. Subsolar clouds are present in all the simulations, which you can see in the yellow on the left, where the latitudinal heat transport is much more significant for the faster rotating planets. So to create phase curves from these static simulation outputs, I created a kind of moving window to sum up the outgoing radiation over longitudes that are visible to the observer throughout each planet's orbit. It's interesting to note from the TRAPPIST-1E results how different its phase curve can be when it has a different atmospheric composition. So far, we've only been talking about phase curves in single planet systems, but what would the phase curve of a planet in a multi-planet system look like? So this figure shows an example phase curve from the TRAPPIST-1 system phased on the orbital period of the outermost planet. And instead of one nice sinusoidal signal, you will instead see the sum of all the phase curves of every planet in the system, which is shown in the dotted black line. So combining the phase curves of the modern Earth-like TRAPPIST-1e model and the Archean Earth-like TRAPPIST-1f model results in the dashed line seen in black. The maximum contrast of this signal is less than 1 part per million, which would unfortunately not be detectable with JWST, nor with future space telescope concepts like HAVAX or LUVOIR. Okay, so with that, I'll put up my summary of my dissertation results, where I helped develop a new detrending method to produce robust exoplanet phase curves. I also measured the first constraint on the average albedo of rocky exoplanets, and also found the first evidence in test data for substantial winds in the atmosphere of hot Jupiter. Then I also used NASA's Rocky 3D GCM to explore the influence of planetary rotation rate on the habitability of terrestrial planets, then used similar models to predict the observability of phase curves produced by simulated TRAPPIST-1 habitable zone worlds. And with that, I guess we can move to the Q&A.
Let's give a round of applause. Well done, Tiffany. Yeah, we're very welcome to any questions from those in the audience. So you can either raise your hand and unmute yourself, or you can type your question in the chat and I can just read it out for you. So if you have any questions, please do raise them. And just to remind the committee, we can ask our questions during the closed portion of the defense. Okay, I can see a question from Maria. What was the rationale in calling the planets Terran rather than the more frequently used term terrestrial? Also, was the choice Terran a nod to Star Trek Discovery?
So the choice was arbitrary, basically, just to sound nice, Terran and Neptunian, I guess. It wasn't motivated by that, but, or maybe it was.
I think that's partly my fault, because that was work that Jing did. And I think we called it Terran because we were trying to include icy bodies and we felt terrestrial was just rock. Anyway, yeah, it's a good point. Andrew Fox wants to know, what are the other possible solvents like water?
So Titan, for example, has liquid methane. So the idea behind a solvent being important is that it facilitates chemical reactions, which lead to, life.
And then another one from Andrew is, how does the planet's influence on the star affect its phase curve?
Yes. Okay, cool. All right, I have backup slides. So one way in which the planet can influence its star is through tidal distortion. So if a massive planet is close enough to its star, it will tug on the star, basically pulling it into a more football-like shape. And when we watch the planet orbit the star, we see the planet's size appear, the star's size appear to change throughout the orbit. And when this happens, the star appears brighter because we're looking at a larger surface area. Another way it can influence this phase curve is through something called Doppler beaming. So when a star and planet are orbiting their center of mass, the light in front of the star gets kind of, it gets beamed, it gets kind of bunched up. And so it appears brighter when it's heading towards us and dimmer when it's heading away. So these can all sum up into like the overall phase curve. But if you have mass constraints on the planet, you can correct for them. So they're relatively easy to correct for.
Mm-hmm. Alex Tichy wants to know, I think I missed it. Why are the TRAPPIST phase curves so small that they can't be observed with JWST, HABEX, or LUVOIR?
Yeah, so this just has to do with them being very small planets. Also, the star is very dim. And also just the size from the star. So in a lot of cases, the phase curves we detect are for planets that are on much shorter orbital periods, much closer to their hotter stars, where we have the opposite case here for TRAPPIST. Farther away, cooler star.
Yeah, it's actually remarkable. TRAPPIST is 10 times further away than Proxima. It's quite distant. Rose Gibson wants to know, can you say something about what your ensemble phase curve results may implicate for our own solar system?
Well, our own solar system is very unlike the systems that we are observing. Of course, there could be multiple planets in these systems that are farther away from their star that we don't see because they don't transit. The probability of a transit occurring decreases the farther away the planet is from the star. But generally, we don't have a planet that is as close to their stars as these systems. So I think what's cool about this is that it doesn't have much to do with our solar system at all, and that we get to observe types of planets that are completely different from the ones we're familiar with.
I think that's any other questions? Okay, I think we'll take one last one. Andrew wants to know, should MCMC be pronounced MCMC or MIC?
Definitely MCMC.
Never heard the Mic pronunciation.
No, my husband's trying to embarrass me in front of everybody.
All right, well, I think with that, we're pretty much getting up to 2:30, so we're about to start the closed portion. So let's thank Tiffany one more time. Feel free to unmute yourself, give a round of applause, and wish her the best of luck.
Woo!
Thanks,
Good
guys.
talk, Tiffany.
Thank you.
Good luck. Talk to you soon.
See ya.
Bye, everyone. Okay, so for those on the committee, I think we have a separate link that we'll be heading over to for the closed portion. So I'll see you all.